Now to better understand this condition here, we need to understand when functions from a metric space into this metric space of linear maps are continuous. What does it mean for a function to be continuous? So let's see if we can break that down in terms of matrix representations for linear maps. So given a linear map, L, from Rn to Rm, if you want to know the components in the matrix representation for L in the standard basis, then what would you do? So let's remind ourselves the notation for our standard basis. We're going to use E1 through En for Rn and U1 through Um for Rm. These will be the standard bases. Then if you want the ij component, of the matrix representing the linear map L in the standard basis, it's the following. So the ij entry, the ij component, is supposed to be in the jth column and the ith row, right? And if I want to know what's going to be in the jth column, then I should apply L to the jth basis vector, like this. And then if I want to know what's in the ith row also, if I want to know in that jth column what's in the ith position, I should look at the ith component of this. So one way to get the ith component, well, what would you do? You would write it as a linear combination of these u's, right? So maybe you would write it as C, I, U, well, let's say C, K, U, K, like this, from K equals 1 to M. And then you would say the ij component is C, Ci here. But there's a way to extract Ci, which is to take a dot product with the ith basis, standard basis vector. So this works because the standard basis is an orthonormal basis. So I can just say dot ui, and that extracts from this M tuple, this is an M tuple. When I dot product it with this, it extracts the ith component. So here is our ij component of the matrix representing L in the standard basis. And I'm just going to come up with a notation for that. Let's call it pi ij of L. So I'm defining a map here, pi ij. For each ij, for each I running from 1 through m, and for each j running from 1 through n, I've got this map pi ij from the metric space of linear maps to the reals. And what it does is, given a linear map, it selects out the ij component of the matrix representing that linear map in the standard basis. Okay, so the first thing I want to look at is continuity for these. If I can prove these linear maps are continuous, then I will know that, so going back to the previous slide here, I will know that if I take a continuous function from a metric space into a space of linear maps, and then I post-compose, or I follow it by pi, then I will be composing continuous functions, and the result will be continuous. So this will be helpful. So the first thing I want to look at is continuity for pi. Okay, so here's I rewrote the definition of pi ij here, and here's our claim that for any I and j that you fix here, the map pi ij is continuous. Proof. So continuous means continuous at every point of its domain. So let's fix a point of the domain. So let let's call it L0. Let that be an arbitrary linear map. And then we want to prove that pi ij is continuous at L0. So for the sake of that, let's let epsilon be greater than 0. And then our goal is to find a delta. So let me leave this kind of a blank here and see what delta is needed. So our goal is to find a delta that works. Maybe I'll just put a box. And works means this is what delta has to do. So if I fix L a linear map such that the distance, using the metric on the space of linear maps, such that the distance from L0 is less than delta, then let me do some scratch work here. What we want is that the distance between these two real numbers, so this is an absolute value symbol here, to be less than epsilon. So let me just analyze this quickly in sort of scratch work mode. Actually, yeah, I think I can just write it into the proof. So I can say then we have this is, by definition, it's LEJ dot UJ minus L0 EJ dot UJ. Now I can pull out the dot with UJ, right? So I can view it as LEJ minus L0 EJ dot UJ. Let me just write it that way first. Oops. So that's fine. And also here, this is L minus L0 of EJ. That's by definition of the pointwise subtraction of linear maps. So the meaning of L minus L0 is that it's this. It sends EJ to LEJ minus L0 EJ. Okay, so now I have an absolute value of a dot product. And there's the Cauchy-Schwarz inequality, which tells us at most how large a dot product can be. A dot product is the largest when the vectors being dotted line up exactly, and then the size of the dot product is the product of the sizes of the vectors. So this is less than or equal to this. And I think we probably never talked about the Cauchy-Schwarz inequality, but I'm considering it to be a linear algebra fact that we allow ourselves to use. And this is one of the standard basis vectors, so this is 1, right? So I can just forget about this. And this is less than or equal to the size of L minus L0 times the size of EJ, which is 1. So this I can get rid of also. By the way, I've been using this a lot. I have used it before, I think, in lecture. I didn't make such a big point about using it. Just to make it clear where that's coming from, let me show you. So here on Rudin page 208, where just after we define the norm of a linear map, it's this observation, this inequality, holds for all x in Rn, that the norm of ax is less than or equal to the norm of a times the norm of x. So that's sort of one of the immediate consequences of the definition of this norm, and I've been using that a lot. And that's what justifies this inequality here. Okay, and this is 1, so we just get that. And that's exactly what we have control over, right? That's what we can make be less than delta. And we want, in the end, to get that this thing we started with is less than epsilon. So now I know exactly what delta should be. It should just be epsilon. So now I have a complete proof. Okay, great. So the pi ij's are continuous. So that tells us something about continuous maps G, let's call them, from a metric space to the space of linear maps. So this is telling us if G, like this, is continuous, where this is any metric space, then these maps, these composites where you do G from X to LRN RM, and then from here to R, so this kind of composition is continuous for all ij. And these maps send X, any X in the metric space that's the domain here, to the ij entry of the standard basis matrix representation of G of X. So if G is continuous from X to the metric space of linear maps, then when you look at these individual real valued functions on X, which are given by extracting matrix components out of G, well then all I times j of these functions are continuous. Now, what about the converse? So now assume G maps is a mapping of this type. This is any metric space. And assume that these matrix entry maps are all continuous. Then can we conclude that G is a continuous map from X to the space of linear maps? So let's look into that. All right, so I've written the assumptions more clearly here. Assume G is this type of map and all the components are continuous. Components meaning maps that pick out matrix components using standard basis. And then we claim that this works. Actually, we can conclude that G is continuous then. So let's see how this works. So first, continuous means continuous at every point of its domain. So let's fix a point in the domain, little x in big X. And then let epsilon be greater than 0. Okay, now let's think about what it is we need. Let me go into scratchwork mode for a bit, and I will delete whatever I write down here in a moment. So assume or want, we want a delta greater than 0 so that whenever y is in the ball of radius delta centered at x, we have that the norm of this difference, which is going to be some linear map, is less than epsilon. So this is, we want to make sure that if y is close enough to x, we can achieve this. So how do we reason about this norm? Well, it's the norm of a linear map, right? So it's defined to be the maximum or the supremum of the lengths of the lengths of output vectors that you get when you input vectors of at most unit length. So what will go in here is a vector with length at most 1. So we'll have to try to do this for arbitrary vectors of length at most 1, and try to get this to be less than epsilon. And then we can conclude that the supremum of all of those, or the maximum, is less than epsilon. So that's the plan. Let me kind of just get us started. And I'm not going to say what delta is right away, but I'll fill it in later. So let delta equal, and then I'll fill in what goes here when I figure out what it needs to be, if it works. If it doesn't work, maybe G is not really continuous, but it's going to work. So assume Y is anything that's in the delta ball centered at X. And now I need to, remember I'm trying to work with this norm of a linear map. So I'm going to plug in an arbitrary vector into this linear map. I'm going to feed it an arbitrary vector of length at most 1. So what should I call the vector? Maybe I'll write it out in terms of its standard basis decomposition. I guess I should use J, since this is a vector that's going to be in the domain of the linear maps I'm talking about here. And I have been using J for that index. So let this be an arbitrary vector in Rn. Get this out of the way. With length at most 1. So such that the length of this vector is at most 1. And the reason I'm writing it out in the standard basis like this instead of just saying, just calling the vector v or something, is because I know that eventually I'm going to want to use this assumption that the standard basis matrix components of G are continuous functions. So I know that I'm eventually going to be breaking things down in terms of standard basis. So it will help. Okay, now let's look at what happens when I take gy minus gx, and I take this linear map and I feed in my arbitrary vector sum over j cj ej. Well, it's a linear map, so I get sum over j cj, and then this evaluated at ej. And hopefully you can see why I would do this now. This is going to be the jth column of the matrix representation of this linear map in the standard basis. So let me write it out in terms of the individual matrix components. So to do that, let me make use of dot products, kind of like I did before, to project something to its components. So the basic principle I'm going to use is if I have any vector w in Rm, then w can always be written as a linear combination of its components along the standard basis vectors. So it can always be written as a sum, rather, of its components along the standard basis vectors, with some coefficients here. And you can say exactly what these coefficients are. They're these dot products. So this is one of these things that works whenever you have an orthonormal basis, and nothing's better than the standard basis for that. So this is the principle I'll be using. For any vector, for any m tuple, you can do this. Okay, so I'm about to use that principle now. And I'm going to apply it to this m tuple here. So I'm going to get a second sum. And I just pulled the Cj out of that, or pushed the Cj into that sum. So I can just write it as a big sum in front. And now I've got this. All right, and this here, this is the it's the ij component of the matrix representation of the linear map gy minus gx, which is the same as as if I took the ij matrix representation of gy and then subtracted the ij matrix representation of gx. Instead of making that kind of roundabout argument, let me distribute things a little bit here. I think that will make the argument more clear and direct. So here I have gy ej dot ui minus gx ej dot ui all times ui. Okay, now it's unmistakable. Let me just write this as a sum over I and j, and you know what I mean by that. It's exactly this double sum here. And now it's unmistakable. These are pi ij gy and pi ij gx. And remember, the pi ij composed with g functions are exactly those functions that we knew are continuous. So we should be able to control each of these. This sum here has a total of n times m terms to it, right? So I'm going to use n times m different continuity statements to control the sizes of all of these. Okay, sorry, I don't know why I used a square bracket in one place and a parenthesis in another. So this is sort of suggesting to me what I should do for my delta to make this work. So first, let me actually go back and turn this into an absolute value kind of statement. An argument about the, sorry, not absolute value, but about the norm of these vectors. So back here, let me insert norm bars in green. I'm actually more interested in the norm of this, which is the norm of this. And, you know, how about I just go ahead and use the triangle inequality right away. So let me make this a less than or equal to, and then stick absolute value here and norm here. So then here, absolute value and norm, absolute value and norm, absolute value and norm. And you know the norms of the CJs, so I don't have to worry too much about the CJs. The CJs are under control just because up here I'm considering an arbitrary vector of length at most 1. So the individual CJs are all in absolute value at most 1. So here I can say this is less than or equal to sum over ij of, and then just this part. What happened to the dot product? Oh, yeah, right. No, never mind, it's fine. And yeah, the norm of, so looking at this norm, well, let me do things one at a time, one step at a time. So in this first step, I'm using the fact that each of these absolute values is less than or equal to 1. That's what justifies this inequality here. Then I claim that I can do this. Well, I can certainly do this and separate them, like this. Then this would be an absolute value. This would be the norm of a vector. And that's just by properties of norms. And then I can do this because the length of a standard basis vector is 1. So now I've got my original thing up here, bounded above by this sum of a total of n times m terms, and these are the terms. And each of these I individually could control by making y close enough to x, because I know pi ij composed with g is continuous for all ij. So now I know what to do for delta. So let me go back up to that box where I had put in delta and fill in this box. Okay, actually, let me zoom way into this box and fill in a detailed argument, because I think more details are needed to decide exactly what is delta. So here's the argument. For each I, let me just say for each ij, you know where the ij's are coming from. For each ij, there is some delta ij greater than 0, such that whenever y is in a delta ij ball centered at x, we have the distance between pi ij g y and pi ij g x is less than, and I'm going to put epsilon over n times m. That's because that sum down there has n times m terms in it. And then here's how I'm defining delta. It's going to be the minimum over all of these n times m delta ij values. Okay, so there's our definition for delta. Now I can do this. So n times m times delta ij is epsilon. Great. So the benefit here, so overall what did I get, is that when I take gy minus gx, when I take this linear map, and feed it any vector that has at most unit length, I get epsilon over here. I get that the length is less than epsilon. So therefore I can say that about the supremum over all vectors of length at most 1. Well, I guess about the supremum I could only say that it's less than or equal to epsilon, not that it's less than epsilon. But since it's also a maximum and not a supremum, I could say less than epsilon. All right, so that proves our claim up here, which is that if you have a function from any metric space to the space of linear maps, and you know that when you view it as a matrix of functions with a function in each matrix position using the standard basis, and all of those individual real-valued functions are continuous, then you can in fact conclude that the overall function g here is continuous. So just to clarify what I meant by that, what I'm talking about is when you have this, you can represent g of x by a matrix for any given x, and it'll be not equal to but represented in the standard basis by a certain matrix with some function of x here, some function of x here, for all of the entries in the matrix. And this matrix will depend on x, so you can think of the entries as depending on x. That's what those pi ij composed with g's are. And what we're saying is this function is continuous. Now we know this function is continuous if and only if each of these individual functions here in the standard basis matrix representation, these are all continuous functions of x.